Hey YouTube, in this video we're going to take a matrix approach to solving a system that we already know or are aware that it's going to have infinitely many solutions. So let's take a look at this system over here. We see that we have two equations and three variables, which we know that if we have more unknowns than we have equations, we're not going to have luck finding at least a unique solution. So I do want to mention this. We do have fewer equations than variables, and also this. This would have been arrived at if we had any system that actually would have given us the result 0 equals 0. And you can see that maybe we had a system with three equations in the first place, and that last one just canceled out perfectly, which we understand to mean that we have infinitely many solutions. But let's just say we were given these two equations and we want to solve this system. Well, I think our method has been thus far to write an augmented system or augmented matrix that goes with this system. So let's go ahead and start with that augmented matrix. In this case, we'd have two rows and then it looks like four columns. And so we'd have in the first row here 2, a 4, a -2, and then we would just have, you could put a line here if you want to, a 0, and then we say, okay, so 3, a 5, no things here, and then one constant over here. So I think our method, what we want to do is put this in row echelon form, and even better would be reduced row echelon form. But let's go ahead and go with row echelon form for now. We want to start with getting a 1 up here. So we'd say, let's multiply this by its reciprocal, 1/2 row 1. So we get this new system here where we'd still get 0 on the right here, and these would be cut in half. So we'd have 1, 2, and -1, and then the second row we didn't do anything to, so 3, 5, 0, and then 1. So now looking at this, we say, well, I've got a 1 here. Let's use this 1 to cancel out this 3. So we'd say -3 times our first row. We're going to add this to our second row, which then makes this underneath it equal to nothing. So we say 1. I know this is going to be a 0. We didn't do really anything to the first row. It's stuck now. And then the second row becomes this. We said -3 times a positive 2 is -6, plus this 5 is -1. And we say -3 times this -1, which is 3, plus 0 is 3. And we say -3 times nothing plus 1 would just give us nothing. Okay. So let's say that we do want to put this in reduced row echelon form, which I think is an appropriate thing here. Since we've got a 1 here and then 0's above and below it, there's nothing above it, but 0's below it. Let's go ahead and move on to this next spot here on this. You could call it, I guess, the main diagonal. And we want to make this a positive 1 itself, so we'll take -1 times that row, so times row 2. So now, nothing new. I mean, same things we've been doing with systems here. We say 1, 2, -1, 0. The second row becomes 0, +1, -3, -1. And then now looking at this, we could say, well, let's use this 1 here to get everything above and below it equal to 0. So perhaps I get this equal to 0 here. And we could see that, okay, if I were to do this, I suppose I would take -2 times row 2, and I would add that on to row 1. So I'll transplant the system over here. But we would say this, our first row now, our second row didn't change in that maneuver right there. 0, 1, -3, and we'll put this line here, and then -1. But our first row, the nice thing about this is since we had a 0 here, this top one is not going to change. People ask, well, won't this change? No, it won't change because this is a 0. We know that this is going to be a 0 now. We kind of caused that to happen. The question is, what is elsewhere? So if we took -2 times this -3, it'd be a 6, plus this -1 is a 5. And then furthermore, we would get -2 times -1 is 2, plus 0 is 2. Okay, so this is our system. And I'm actually going to stop here because what I want you to see is this would be considered to be row echelon form. We tried to get it in reduced row echelon form, but we couldn't because of these things over here. But it's definitely in row echelon form. And what I recognize is if I were to put my variables back in, we've got an x, y, and z column, and then this is like our, some constants over here. We would see that we have a system that says x plus 5z is equal to, and that's a 2. And then we would see that the second equation, we get 1y minus 3z is equal to -1. And we could see that there's no way we're going to be able to eliminate this down to like one variable type. But the one thing that they both have in common is z. So now if you put this into reduced row echelon form, row echelon form at the very least, we can at least say this. We need to choose a parameter for one of our variables here, and it's typically z. Because what we're saying we have here is this. We have a couple of linear planes. This is what these are when you graph them. Say I have another plane cutting across here. And they just like cut across each other. And actually, if you were to extend these planes forever and ever, they cut across each other on this entire line. We need to find all of these points, all infinitely many of these x, y, z's that make these two things true. So what we're going to do is we'll say this. We'll say let z, for instance, here equal a real number a. Let's just let this be true. Okay. So if I knew that this was the case, then we would say this point right here, we could actually label it. We could label it z value of a. And then we say, well, if z is a, what we're going to do is we're going to back solve now. We say y minus 3 times a is equal to -1. I'm just plugging that a in right here. And we say then y must be -1 plus 3a. So -1 plus 3a is our y value plus 3 times this input a. And so we say y equals, I'm going to write it up here also, kind of organize them all together. And we say, so now what is x? And so x, if I wanted to find x, well, I already know z. I could go plug that back in up here. And we see that when we get this, we say x plus 5 times a is equal to 2. So x is, of course, 2 minus 5a. And so these three, in this ordered triple, these three values, okay, represent the x, the y, and the z value if a was equal to our z value here, where we would have solutions. So we would just label this as solutions. But what this looks like in a matrix here is you see that you had fewer, say, rows than you had columns. It just means less equations than you have variables. Cheers.